So we've got this cart that is on a spring. There's no friction basically, and we're gonna pull it all the way back here to A and let it go. And whoom, it's obviously gonna zoom back towards C, overshoot that, come back to E, and it's gonna stop and then be pushed back out to C, and the whole thing is going to repeat over and over again. They're calling to the left of C negative here and to the right of C positive. And the first thing they said, they wanted a position diagram for the motion between points A and E. So we pull out here again, we let it go. It's going to start to go over here where it comes to a rest. So another name for this is a dot diagram. So let's say it's like dripping little bits of oil every 1/10 of a second or whatever. So we let it go at A. Right when it lets the drip go, well, it's going to start to pick up speed. So it's going to move some little distance more and make another drop, but then it's going to pick up speed even more. So it's going to make another drop further out. And then it's going to move out even more by the time it's at B and even move further out. And then even more speed, a greater distance between dots there. But once it gets to C, then it's going to slow it down. So we're not going to pick up an even greater distance. We're going to be back to this distance because the spring's pushing out on us and slowing us down. And then it's going to slow us down even more and slow us down even more until we finally come to a rest right there at E. So the distance between the dots here increasing shows that the velocity is increasing, and the distance between the dots here decreasing shows that the velocity is decreasing. Then they wanted a bunch of free body diagrams. Well, to draw every single one on camera would take forever, so I went ahead and added some of the most important things. Notice the force of gravity is the same in every single picture because the mass of the cart's the same, and it's here on Earth. And correspondingly, the normal force counteracting the force of gravity in every single diagram is the same. Now, to realize what's going to go on here, we need to pay attention to Hooke's law. So Hooke's law says that the force the spring pulls with, we could put a little s there, is equal to the spring constant times x. So let's say we come out here to some distance. If we're out here at A, then we're going to be pulled back to the right. Some books put a little negative there to indicate that whatever the displacement direction is, the opposite of that is the direction of the force. On our equation sheet for the AP test, they put absolute brackets around there. Well, what about at B? Well, B's not displaced as much, so the spring, the x is smaller, so it's going to pull with the smaller force there. So whatever you drew for A, B's got to be a little bit smaller. At C, we have no displacement, so we have no force there. At D, now we're on this side. We're compressing the spring, so the spring is going to pull us back out. So whatever distance you had here at B, it should be the same for D, just pointing now to the left. It's trying to push it back out. And then whatever you had for A, you should have that same distance here for E. So E again should be larger than D, and it should be equal to A there, just pointing to the left. And so that's right where it gets to E, and then it stops, and then it shoots back out. So actually, time-wise, we go this direction, and now we're back down to here. Well, once we start to move the other way, it doesn't matter what way we're moving. This says nothing about what way we're moving, nothing about velocity, so it's still going to be pushing it to the left. And by the time we've moved out towards D, now we're going this way at D. It's going to be still pushing to the left and making it pick up speed, but pushing with less force. No force at C again. By the time we overshoot now and we get back to B, now we're here, the force is going to be pulling us back towards the middle again. Force is always towards the middle in simple harmonic motion. It's restoring. So back towards the middle there, same value as up above, and then once we get all the way out to A, we've stopped now here again, and we're pulling with a maximum force to the right. So the next part says, do the diagrams above indicate whether the car is moving to the left or to the right? Justify your claim with evidence. Well, no, they do not, and let's just look at it here. So the picture, whether we were moving right or moving left, doesn't really matter. By the way, saying that it's moving right at the ends here or moving left, it's a little bit weird because it's actually not moving at all, but it's getting ready to move right here. And it just stopped moving right here. And it's getting ready to move left here, and it just stopped moving left here. But the point is the velocity is not indicated on that diagram at all. So let's sort of keep that picture here a little bit as we start to fill this in. Well, how to put it here. It says, what is the direction of each of these? Displacement's easier. At position A, you can clearly see it is to the left of center. We could call that a negative direction like they do. At position B, we're also to the left, or negative if you want to call that, and here there is no displacement, or you could say 0. At position D, we are to the right of what they call the center, or we could say that that is a positive, and same thing at position E there. What about then the direction of the force? Well, again, Hooke's law is always going to say it's going to push you back towards the middle. So if we are to the left, then the force is going to be to the right, and say that that is positive. At position B, again, it's still going to push you to the right, which is positive. No push at all at C. And at D, it is going to be pushing you back to the left there, which is a negative direction for the force. And at position E, it pushes you to the left, which is negative. So notice that the force and the displacements are always opposite. So going back to the picture one last time, whenever you are displaced negatively, you will be being pushed positively. And whenever you are being displaced positively, you will be pushed negatively.